Greetings and welcome to my channel. I'm Armin, and this video is about propeller noise in ANSYS Fluent. I always use Fluent with Fluent meshing, and I suggest it for propeller modeling. I'm going to import a propeller and prepare it for CFD analysis. Then, I'm going to enter the space claim and create two domains. First, we need a rotating domain. The size of the rotating domain should be approximately equal to the size of the propeller. Four millimeters is a proper size. We don't need the propeller geometry, and we need to delete it. This is a very important point. We don't need separate components, so I'm going to delete components in the structure tree. It is advisable to select a name for the rotary domain. We have to define the propeller surface as a wall. Therefore, I'm going to hide the outside surface of disk. The propeller surfaces are the wall, and I'm going to name it. We can see the geometric dimensions from this here. The next step is creating a stationary domain. The diameter and height of the stationary domain should be at least 10 times of propeller diameter. As you can see, the propeller domain has been recreated. We don't want it, and I'm deleting it. Like before, I'm going to choose a name for this domain and delete component. We have to specify the inlet and outlet of air around the propeller. Rotating and stationary domains must be coupled by clicking on the Share and Workbench tab. Blue lines indicate interfaces between domains. Geometry is ready to use. Now we can close Space Claim. Okay, it's time to generate mesh. So I will open the mesh and check the double precision box. This is the workflow module. First, I'm going to click on Import Geometry. In Add Local Sizing, I will specify a face mesh for rotating domain surfaces. The next step is adjusting the surface mesh size. I will reduce the curvature angle so that the mesh better fits the lead and trailing blades. If the minimum size is large, it encounters an error. We have to describe geometry in this way. There is no solid in geometry. There is no wall between the rotary and stationary domains. I want to calculate propeller noise in stationary, so I'm going to define a pressure outlet for the inlet boundary. The fluid region name indicates propeller volume, which I deleted. I have to change it to dead, because it's not a fluid structure interaction problem. The boundary layer is essential to adjust IPLS. I'm going to specify 5 micrometers for the first height layer. Polyhex core is the best cell shape for aeroacoustics analysis. I leave all default options. Here, we can see the number of cells. Only the quality of one cell is low, so we can leave it. We can close the mesh window and go to Setup. First, I need a stationary solution, so I leave General and Models. In Cell Zone Conditions, I'm going to select Frame Motion, which indicates the MRF approach. Also, I'm going to specify an optional speed. In methods, we have to select Simplex for stationary and Piezo for transient solution. Please specify spatial discretization like my way. Under relaxation is too low. According to my experience, 0.5 is okay. Finally, I'm going to click on Initialize. In the last step, I'm going to click on Compute. Solution has been completed. Now we can see the value of IPLIS. We can see the velocity contour. I'm going to create a plane to see flow velocity. I had wrongly determined the direction of rotation of the propeller. I should have added a minus before the number. This is an educational video, so I will ignore this mistake. I want to calculate noise, so I have to select Transient Solver. We can use a simple way to convert frame motion to mesh motion. In the console, I press Enter. Then, I'm going to type mesh. Now I'm going to type the modify. By typing MRF to sliding mesh, all options are adjusted automatically. After typing, Fluent asks what domain must be converted to sliding mesh. I'm going to type the ID of the rotary domain. Here we can see mesh motion. Also, mesh interfaces have been created automatically. Now we can select the desk model. In the method, we have to select bounded second order. Basically, piezo is chosen in the transient solution. However, I will choose simple C. The time step must be small enough to converge the solution. By this time step, we can see the solution up to 5000 Hz. First, I want to check convergence, so I enter 5 steps and see the answer. The solution has been converged, so we can set up acoustics. In acoustics, I'm going to select Ffowcs Williams-Hawkings. I recommend ASD format for exporting solution. In describe sources, I'm going to select propeller walls. In describe receivers, we can install microphones in the desired location. Acoustic has been added in post-processing. The minimum time required for the Aeroacoustics solution is 0.1 seconds, so at least 1000 steps must be solved. After 10 steps, I stop the solution. For exporting acoustic solutions, I will click on Acoustic Signals, select all options, and click on Compute. We have to go to Results to see acoustics results. By clicking on the chart, we can create a pressure acoustics plot. We must check the transient or sequence option because we want to use fast Fourier transform. From here, we have to find receivers. Here you are. This is the diagram of sound pressure with respect to time. Also, we can plot sound pressure level with respect to frequency. I have a bonus for you. Please watch it. Here I will show you how to create a body of influence. First, I have to hide the stationary domain and draw a cylinder. By doing so, the body of influence and the stationary domain remain separate. I'm going to mesh and add a body of influence. We can see new cylinder here. We can specify our desired cell size by selecting the body of influence. We can see the effect of body of influence on the mesh. The propeller now rotates in the correct direction. Mesh size is coarse. I would greatly appreciate it if you like and subscribe to my channel.